recording. Okay, so last time we kind of made a jump into linear algebra up to lecture number 6. We've been dealing with matrices pretty extensively. We talked about row reducing matrices. We talked about elementary matrices. We talked about how to find the inverse of a matrix, and finding the inverse of a matrix helps us in solving the system of equations that is transformed into a matrix equation. We talked about invertible matrices a whole bunch. And so then we went into a different realm now. We went into a world of transformations, right? So that's one thing that was new from last time. So just to recap really quick, recap of lecture number 6. The main concept that we spoke of is a transformation, right? In particular, we're talking about a linear transformation. So it's a what? It's a function, right? This idea of functions pervades mathematics, and this is a function that maps, right? That maps an element, or you can call it a vector, or n-tuple. That's another word we talked about, right? An element or a vector. Call it U in Rn to an element. I'm gonna call it X. X in Rn to an element or a vector. Y in Rm. And then we're talking about this idea of n-dimensional space, m-dimensional space. We're accustomed to the real line, right, which is R1. We've been very we've dealt a lot with the XY plane, which is another two-dimensional space, right, R2. And then we talked about the XYZ space, which is R3. And then we start talking about R4, R5, R to the 10, and Rm. So these are spaces where everything in this space, right, are n tuples that have n entries in the vector. And same thing goes for this guy. It just has m entries. They could be the same number, or they may not be. And then we have this notation here, T. So I'm going to just insert this here. The linear transformation, we call it T, right? And it takes Rn and maps it to Rm. And we've also discussed the domain is denoted by the first set, right? And we put a little arrow to indicate that we're mapping this domain into the space of its codomain, which is associated with the range, right? And then we also have a notation saying that if we treat x as an input and as t as a function, the result gives us y, right? And this is like a general way of discussing what a function is. For you guys, a function was really just r to r, right? So an example of that would be like f of x equals x squared, for example. I took a point in r and I mapped it to something in r as well. And of course, if you graph this is in the xy plane. But now we're dealing with things that may be in 3-dimensional space, and I want to map it to something in 5th-dimensional space. I took something in 3rd-dimensional space and map it to something in 7th-dimensional space. So that's where we're headed. And for every linear transformation, the fact that it's linear, right, we have properties. We have certain properties of linear transformations. So in order for something that's called transformation to be linear, you need two things. The first thing is that if you take a sum of two vectors in one-dimensional space in a Rn, and you plug it into the transformation, the result should be the transformation of u applied to u individually plus the transformation of v. So that is one property of what it means to be a linear transformation. And then the second property is that if you have a scalar multiple of a vector, and you're trying to transform the scalar multiple of that vector, it would be the exact same thing if I took the transformation of that vector first and then applied multiplying by that scalar. So these two properties are very important because they indicate whether or not a transformation is linear. If the transformation abides by these two properties, then we say T is linear. Okay, so the properties that don't abide by these properties would mean that it's not linear. And what's cool about linear transformations is that there are matrices that are associated with that transformation. So then that's where we have associated matrices, right? Of linear transformations. And that's how the matrix concept comes into play into this transformation concept. So every linear transformation, right, can be expressed as a matrix. So there is a n by m matrix called A associated with linear transformation T, where T goes from Rn to Rm. Oh, pardon me, this should be the other way around. This should be m by n. So remember that? So if I took something in Rn and I result it, and the result is something in Rm, then there exists, it's the same thing as if I were to take a matrix A, left multiply it by x, and give me y. It's the same idea. And this, if x is an n by 1 column vector, then this would have to be an m by n matrix, which results in an m by 1 column vector. Okay? So we talked about that. And then briefly in the previous, in the last lecture, what we saw is we can actually find the matrix A of a transformation. We were able to find it. And how do we find it? Does anybody remember how we find a matrix A if you have a given linear transformation? So for example, I think this is the example that we had, right? So if we have a transformation T that goes from R2 to R3, and we say that T takes x1, x2, and gives us something of the form 2x1 plus x2, comma, x1 minus 3x2, comma, negative x1 plus x2. So I have this transformation here. Does anybody remember how we are able to figure out what is the matrix that's associated with this linear transformation? What was the simple two steps that we needed to do?
Was it that you had to plug in E1 and E2?
Right. So what you do is you find the image. Remember, this is another term that we discussed too as well. Find the image of the standard basis vectors. That's another thing we talked about, right? The standard basis vectors in R2, the image of standard basis vectors. And these are E1, right? Which is 1, 0, and E2, which is 0, 1. So what does that mean? Find the image of standard basis vectors R2 under T. In other words, what that means is find what T of E1 is, and then find what T of E2 is. So that image, the image that you get, which is the result of applying E1 to the transformation, what does E1, where is E1 being mapped to in R3? That's really the question. If I take E1 from R2 and I put this I put it under this transformation, where is E1 being quote unquote mapped to in R3? So that's where you apply it, right? You apply the you apply 1, 0, and this becomes 2 times 1 plus 0, comma 1 minus 3 times 0, comma negative 1 plus 0. And that would be equal to 2, 1, negative 1. So E1 is mapped to the vector 2, 1, negative 1 in R3. And then a 0, comma 1 is mapped to 2 times 0 plus 1, 0 minus 3 times 1, and negative 0 plus 1, which would give me 1, negative 3, 1. So E2, the standard basis vector in R2, is being mapped to the vector 1, negative 3, 1. So for the matrix, right, because these two statements can be now expressed as a matrix multiplication being applied to the left of the vector. So TE1, I can represent this as some matrix multiplied by E1. But if you understand matrix multiplication and the fact that you're multiplying by a vector that is 1 by 0, right? So when I apply this vector here, I really get what? I get 2, 1, negative 1, right? But this means that this is the first column of A. By applying this left multiplication of A on the left of 1, 0, and this is a 2 by, this has to be a 3 by 2 matrix, then the first column must be 2, comma 2, 1, negative 1. And then the same thing goes for TE2. Get 1, negative 3, 1. So this is the second column of A. So A is equal to the column, the matrix 2, 1, negative 1, and 1, negative 3, 1. Now, what this means is that give me any other vector. Give me any other vector in R2. So like give me the vector. So suppose now I want to find, suppose I want the image of the matrix, the vector V, right? I'm gonna call this V a 1, comma 2. Where does 1, comma 2 go under T? Where does it go? So I'm going to apply T, right, of the vector V. I'm going to apply this. This is T of 1, comma 2, right? But what this now means, I can do this 2 ways. So I'm going to do 2 ways. I can do this in 2 ways. I can treat this as a matrix multiplication of A. or I can treat this as a linear combination of the standard basis. Vectors of R2, which is E1 and E2. So I'm going to do these in two different ways, and I should get the same answer. I will get the same answer. So then T of 1 comma 2 can be written as what? A multiplied by 1, 2. But what is A again? A is 2, 1, negative 1, 1, negative 3, 1. And I'm left multiplying this by 1, 2. So when I perform the matrix multiplication, I get what? I get 2 times 1 plus 1 times 2. I get 1 times 1 minus 3 times 2. I get negative 1 times 1 plus 1 times 2. And then 2 plus 2 is 4. 1 minus 6 is negative 5. And then negative 1 plus, pardon me, it's not a multiple. This is not decimal. So negative 1 plus 2 is 1. So this is the image of 1 comma 2 under this transformation. I get 4, negative 5, 1. That's where that vector 1 comma 2 in R2 is being mapped to in R3. Now, how do I deal with this as if it were a linear combination of the standard basis vectors? So again, V, right? V is 1, 2. Now, how can I rewrite this as a linear combination of E1 and E2? Does everyone understand what I just asked? Okay, good. Thank you. So I'm asking, how can I rewrite 1, 2, right? The vector 1, 2 in terms of E1 and E2. So this should be a simple way. This should be a simple task.
It would be one times column vector 1, 0.
Right, which is E1.
Oh yeah.
Right. And then plus?
Plus 2 times E2.
Right. Do you guys see that? Because like, remember what we talked about standard basis? The standard basis vector is basically the two vectors in R2, right? That are like the most elementary vectors there. So that every other vector that I have in this space can be rewritten as a linear combination, which is what this is, of E1 and E2. I can express any vector in R2 using E1, enough of E1s and enough of E2s that when you add them up, I give you that vector. If you don't see that geometrically, you can see that arithmetically, right? E1 is 1, 0, and E2 is 0, 1. So if you have 2 0 1s and you have 1 1 0, when you add these up, you get 1 2. Now, why does that matter? Because I want to figure out what T of V is, right? But then I just expressed it as a linear combination of E1 and E2. I can rewrite this as T1 E1 plus 2 times E2, right? Isn't this the same exact thing? That equals V. That expression E1, E2 equals V. But then T is what? What is T? T was, the way T is expressed is a linear transformation. Because it's linear, I can rewrite this expression as using the linear properties of a linear transformation, which would be what? Which would be that I can do these individually. 1 times E1 is just E1. I can do these separately and add them later. And then because there's a scalar in front of the E2, I can rewrite this as 2 times E2 plus T of E1. And why is this so good? Because I already know what T of E1 is. I know the image of TE1. Don't I know that already? Isn't that 2, 2, 1, negative 1? And I already know what E2 is mapped to as well. It's 1, negative 3, 1. So this is 2 times 1, negative 3, 1. And so when I continue with this, right, this is 2, 1, negative 1. When I multiply the vector 1, negative 3, 1 by 2, I get 2, negative 6, 2. And when I add this, what do I get? I get 4, negative 5, 1, which is exactly what I got in the previous solution. So do you guys see how either way that I view this expression as either a matrix multiplication of A or as a linear combination of standard basis vectors, I get the same exact thing. Because they are the same exact thing. They're just viewed from a different vantage point. Here I'm dealing with the standard basis vectors, E1, E2. Could you just break quickly? Yeah. Yeah. So again, what am I doing? What am I doing? I'm just going to break it down from the beginning, right? I'm given a transformation that goes from R2 to R3. And this is the way that a vector in R2 is being mapped to something in R3. This is the rule, right? So the first entry in R3 would have to be a combination of X1 and X2, and then so on and so forth, right? And the first thing I want to do is figure out, or what is the associated matrix of T? Since this is a linear transformation, there has to be a matrix A that's associated with this linear transformation. And how do I do that? Well, I apply E1 and E2 to this function so that I get the image of those two basis vectors. Now, once I have that, then I can find the matrix A. I know the matrix A. The first column of A is given by the image of E1 under the transformation, and the second column of A is given by E2 of the transformation. And I was able to do that. Now that I have the associated matrix of A of the transformation T, I have this new little task. I want to figure out what is the image of V under T. So what if I get a new vector 1, 2 in R2? I want to know what that is when I apply it to T to it. Where does 1, 2 go to in R3? What's that vector that's associated with 1, 2 under the transformation T? I can view this in two different ways. Either I can just say, hey, you know what? Let me just left multiply 1, 2 by A. And that gives me the vector 4, negative 5, 1. So if I were to take 1, 2 under T, I get 4, negative 5, 1. In other words, 1, 2 is being mapped to the vector 4, negative 5, 1 when I apply the transformation T to it. That's one way to view this transformation. Another way to view it is if it were a linear combination of the standard basis vectors of R2. So suppose, as you can tell, I don't even need to know the transformation, the matrix A to figure this out. All this is required, all this is based upon is understanding the image of E1 and E2 under the transformation. In other words, I want to figure out, where does E1 go to when I apply T to it? And where does E2 go when I apply T to it? And that's exactly what I did here, right? I plugged in E1, which is 1, 0. I plugged it in and I found this is what E1 goes to when I apply T to it. And then what does E2 go to when I apply T to it? It goes to this vector. So once I know the image of the standard basis vectors in R2 to R3 in this example, then you can give me any vector. It doesn't have to be this one. You can give me any vector in R2, and I know exactly what that vector will be mapped to under T, because I know what E1 is mapped to, and because I know what E2 is mapped to. And once I know what E1 and E2 is mapped to under T, I can just express V as a linear combination of these standard basis vectors. That's what it means to be a standard basis vectors. And we'll talk about a basis vector in the future a bit more extensively. But for now, all you have to worry about is that standard basis vector. A standard basis vector is the vectors, right, that have a 1 in one of the entries and zeros along the other ones. So in R2, the only two standard basis vectors are E1 and E2, and that's it. There's no other set. These are the only two vectors. So because I know E1 and E2, every vector in R2 can be expressed as a linear combination of those two vectors. And it's pretty straightforward, right? I need one E1 and I need two E2s. When you add them up, I get 1, 2. I get 1, 2. Now, because I'm able to express V as a linear combination of E1, E2, then when I apply T to V, it's the same thing as saying T, applying it to the linear combination of E1 and E2. Because T is a linear transformation, I can apply the properties of linearity, which means that I can take the sum of the two vectors and split them up and take the image of those individually. And then I apply the second property of linear transformations, which is now, if I have a scalar multiple of a vector, I can just take that scalar and multiply it out, or I multiply it after I find the image of E2 under T. So then really it becomes just the image of E1, which I already know what it is, T1, 2, 1, -1. And I add it to double whatever E2 goes to, which is 1, -3, 1. And then from here, it's just adding two vectors with the scalar multiple of one of them. And 2 times 1, -3, 1. You multiply every entry here by 2, and I get 2, -6, 2. And then I add these two vectors, and I get 4, -5, 1. Does that make sense? Right. So then there's two ways to view this. That's all I'm trying to say. One way is as a linear combination of E1 and E2. And the other one is as a left multiplication of a matrix. Regardless, though, in either scenario, the notation can be confusing. It can, because they seem to be different, but then they're the same, but then they're different, but then they're the same. They're the same exact thing. If you notice this here, it's here. Like they're the same thing. These are exactly the same. It's just that it's viewed differently. You're viewing this as a left matrix multiplication of a matrix to a vector. Here you're viewing this as a linear combination of the image of E1 and E2. Okay. Yeah, T of E1 is not E1. T of E1 is 2, 1, -1. But my main point, regardless, my main point for this example and for the other ones that you'll see in your homework, or some of you have done it already, is that once you know the image of your transfer of the standard basis vectors under the transformation that you have, once you know where that E1 is being mapped to, where that E2 is being mapped to under this transformation, then any other vector that you can think of, because you're able to write it as a linear combination of those standard basis vectors, you can figure out where that vector is being mapped to, given the fact that you know where E1 goes to and where E2 goes. So once you know those two things, then you can find any vector in R2 and where that's being mapped to under T in R3. That's the whole point. So once you're able to find the image of the standard basis vectors, you know every other vector. Okay. Any other questions about this? Does that make sense? Yes. Okay. So then the other kind of problems that you'll see in your homework and the last three or four problems in your homework has to do with the following. So yeah, it's this kind of example. Find the standard matrix A for the linear transformation T, and T goes from R2 to R2. for which t of -1, 1, when I apply t to this, I get -5, 5. And when I apply 2, -1, I get 7, -6. Now just remember, just to recall, when you have a transformation, a linear transformation that takes one vector from one space and maps it to the same space, so R2 to R2, we call T not just a linear transformation, it becomes what's called a linear operator or just an operator. So we call them operators. Whenever you have a transformation that maps something, the codomain is equal to its domain. They're the same. Okay. Now, how do I find that matrix A? Or in particular, a standard matrix A. Remember, the standard matrix is associated with the standard basis vectors. Okay. So it's kind of like going backwards in a way. We're kind of going backwards. Normally we have E1, E2, and then we know what the image is. But in this case, we're not given E1 and E2. We're given some random vector. We're giving some random vector. I'm gonna call this V. And I'm gonna call this U. Okay, we have these two vectors. But I want to know what the standard matrix of it would be. So the idea is there has to be a way to express V, right? So express V as a linear combination of E1 and E2. So express V and U as a linear combination. So what is V going to be? V is -1, 1. So how would you write -1, 1 as a linear combination of E1 and E2? This should be quick, guys. Hopefully we now understand.
We would do it like we did it before.
Mm-hmm.
Yeah, negative E.
Negative E what? Negative
One.
E1?
Yeah.
Plus?
Plus.
That's right, Sam. E2, right? And then what's the next one? U would be expressed as what? Right. So 2E1, right? Minus E2, correct? So now that we have this, right? Then can I rewrite? So let's rewrite. Let's rewrite the following. T of V is really what? T of -E1, right? Plus E2. And this will equal negative T of E1 plus T of E2. And this will have to equal what? -5, 5. And then T of U is equal to T of 2E1 minus E2, which equals 2 times TE1 minus TE2, right? And that equals, what does that equal again? Oh, 7, -6, right? So that's one way to represent it, right? Now, remember, to find standard basis, standard matrix A, what do we have to do? We have to find T of E1, right? Get to know what that was. That would give me the first column of A. And T of E2 would give me the second column of A. That's really the goal. What is T of E1? Because I don't know what this is, right? I don't know what this is. I don't know what this is. I don't know. If I were to know, then I can figure out the matrix. So that's what I'm looking for. But what do I have? I got V and U instead. I don't have E1 and E2. And I know what V is mapped to. I know what V is mapped to. It's -5, 5. So the idea behind this, the idea is now to kind of reword this in a way is find the linear combination of E1, E2 in terms of U and V, or V and U. Do you guys understand what I'm asking? Normally, I would ask, what's U in terms of E1, E2, which is what we did, right? This is what we would normally do. V is this linear combination of E1, E2. U is this linear combination of E1, E2. Now I'm doing the opposite. I'm going the opposite way. Now I'm saying, find the linear combination of E1 in terms of V and U. So what I'm saying is, what is E1 as a linear combination of U and V? Do I know what that is? No. So then what I do is I write it as A of U plus B of V. I'm trying to figure out what U and B, what A and B are. I don't know what these are. And then I want to find E2. What is E2? In terms of, so this is a different scalar, right? And a different scalar. Does everybody see that? So let me put this over here. So if I write this out, what is this? This is 1, 0 equals what? A, what is this? U is -1, right? So this is A of -1, 1 plus B of, what is B? Sorry, U, 2, -1. And B and V is -1, 1. So when I write this out, this becomes 2A, negative A, plus negative BB. This is 1, 0. And in other words, 2A minus B, negative A plus B, that gives me 1, 0. In other words, 2A minus B equals 1, and negative A plus B equals 0. Do you guys see that? In other words, I can write this as 2, -1, -1, 1, and create a new matrix equation like this. So either I solve this matrix equation here for AB, or I can just solve this by linear system of equations.
Professor,
Yes.
can you scroll up a little bit? I was lost a little. Yeah.
Where? Where exactly? Do people follow what I'm doing? If you're lost, please tell me. And exactly where? Where is it that?
I know. I just need to write down write down the notes.
Okay. So, can we quickly find the matrix, the inverse of this matrix? Does anybody know how to find the inverse? What would be the inverse of 2, 1, negative 1, 1? Well, remember so if I have a matrix A, right? And this is A, B, C, D, then the inverse would be 1 over AD minus BC being multiplied by, I switch the diagonal entries and I negate the off diagonal entries, the other diagonal. Okay, this is just in general, right? So the inverse, and we should know this. So the inverse of this matrix would be what? Would be 1, 2. You negate the entries 1, 1 on this side here. And then you would multiply 2 by 1, which is 2. Multiply 1, negative 1, which is positive 1, and subtract it, right? This would be 1 over 2 minus 1, which is 1. So this is really this is the inverse. So if that's the inverse, then what is AB going to be? AB is going to be the inverse multiplied by 1, 0. And when you multiply it, what do you get? You get 1, 1. So what is A? A is 1. What is B? B is 1. Now, why does that matter? Why does that matter? Because I need one of these, and I need one of these. So when I add these up, I get 1, 0. Does everybody see that? So A equals 1, B equals 1. So to follow this, right? So So what is T of E1? That's really the question, right? What is T of E1? Well, it equals T of U plus V. That's what I needed, right? I needed, how many U's do I need? I need one of them. How many B's do I need? I need one of them to give me E1. Then if I know this, then don't I know what T of E1 is? It's going to be T of U plus T of V. And why is that good? Because I know what T of U is. I'm given that in the beginning. T of U was what? 7, negative 6. I know this. I know that T of V was what? Negative 5, 5. So when I add these vectors up, I get what? I get 2, negative 1. And that was what? T of E1. And this becomes what? The first column of standard matrix A associated with linear transformation T. That's what we just did. We did all of this extra matrix equation work to figure out what are the scalar multiples of U and V so that I get E1. So that once I have that linear combination of E1 in terms of U and V, because I know the image of U and I know the image of V under T, I can figure out what the image of E1 is. And once I figure out the image of E1 under T, then I have the first column vector of the associated matrix A. Does everyone follow me with that? So I only have the first column of A. I need the second column of A. Now, what do I need to do? I do the same exact thing that I did here, except now I'm using E2 instead. So it's the same idea. E2 is 0, 1. I want to figure out what C and D are. Sorry, this should not be a vector here. This is a scalar. I want to know what C and D are. So I know U is what? 2, negative 1. I know B is what? Negative 1, 1, right? So this becomes 0, 1 equals 2C minus C plus negative BB. When I combine this, I get what? I get 2C minus B, and I get negative C minus B. Sorry, this should be D. Got my B's mixed up. So minus D plus D equals 0, 1. And then if you can write this as an equation, I get 0 is equal to 2C minus D. And I can write this, I'm gonna write it the other way, right? 2C minus D equals 0. And I got negative C plus D equals 1. Or I can rewrite this as a matrix equation. 2, -1, -1, 1, CD as a column vector, and I get this as a column vector, 0, 0, 1. I can write it like this as well. So then what would be the matrix equation for this? Do you see how this matrix here is identical to this? It's the same. So I have the same inverse. So CD is equal to the inverse of this matrix, which I already found to be 1, 1, 1, 2. And now I'm just applying 0, 1 to it. And when I do that, I get 1, 2. That's CD, which means C has to be 1 and D has to be 2. So if I have one U vector plus 2 V vectors, I get E1. That's what it's saying. So now, because I know that, T of E2, which is what I want to figure out, so I can find the second column of the associated matrix, this is equal to T of C, oh, pardon me, not C anymore, 1 U plus 2 V's. That's what E2 is. And I can rewrite that as T of U plus 2 times T of V. T of U is what? 7, -6. T of V is what? -5, 5. This becomes 7, -6 plus -10, 10. When I combine this, I get -3, 4. And so what does this represent? This column vector represents the second column of standard matrix A associated with linear transformation T. Okay, so what is A then? So the standard, so finally, the standard matrix A of T can be written as the 2 by 2 matrix, 2, -1, -3, 4. So this one took a little bit longer than most of the other problems when you talk about the transformations. And what you'll learn in the future is that a basis vector set, a set of basis vectors, there's actually many sets. There's different kinds of pairings. For example, in R2, there's an infinite number of ways to represent a vector or a basis vectors for every n-dimensional space. So the standard basis is always 1, 0, 0, 1, right? But for example, these two vectors, 2, 1 and -1, 1 is another example of a basis vector. It's not a standard basis vector because it's not 1, 0, 0, 1, but it is a vector, a basis vector. 2, -1 and -1, 1 is also a basis vector. So we'll explain a little bit later what it means to be a basis. But for now, it's enough to show that once we have E1 and E2, we have the matrix. So what we had to do here was represent E1 instead as a linear combination of U and V, and represent E2 as a linear combination of U and V. Normally, we have E1 and E2, and we just rewrite the new vector in terms of E1 and E2, and doing that is very simple, right? Because E1 and E2 are simple vectors. But when we're trying to do the other way around, when we're trying to express E1, which is a simple vector, as a linear combination of other vectors that we may not be so simple, then this problem actually in itself becomes a system of equations problem. Do you see? And we had to do this twice. And all we wanted to figure out was what are the scalar multiples of u and v individually that give us E1 and E2. So we found that we needed one of these and one of these. One u vector plus another v vector would give me E1. And I found out that one u vector plus two v vectors would give me E2. And once I'm able to find a linear combination of E1 and E2 in terms of u and v, then finding what the image of E1 is straightforward because I know the image of u and v. And what the image of E2 is, I can find it as well because I know the image vectors of u and v as well. Does that make sense? Any questions about this whole procedure, this whole task?
Professor, could you just scroll up a little bit?
Scroll up.
Right there. Thank you.
Yeah. So any questions, guys? Any comments about this? We're definitely stepping it up now with the whole transformations and matrices, linear combinations. So these words, phrases will appear very frequently. And always try to see, like I think I mentioned this before, right? Always try to see the bird's eye view of things at the same time, the microscopic view of things. So sometimes people get lost in like all of this notation, but try to always visualize or try to see the bigger picture. Is there a shortcut way? A shortcut. Let's see. Well, it almost is a shortcut when you're up to this point here. We're utilizing the fact that you can rewrite this as a matrix equation. So this would be my shortcut. This here, solving this equation is the shortcut. So in other words, no, there isn't a shortcut way. Like this task here, doing this is not an easy thing. Finding the coefficients, right? The scalar multiples of u and v, that problem in itself is not necessarily an easy problem. Like you would have to create this matrix equation and solve. It's not there's no easy way to do this. The other way is easy. The way that we normally would do, right? This is easy. Once we have E1 and E2, it's easy. Finding the vector of finding the image of another vector. Once I'm given E1, E2, it becomes straightforward. It becomes quick. But when it's the opposite way, when it's the other way around, when we're given the image of some vectors that are not standard bases, and we want to find a standard matrix of that takes a little bit more time. Because the reason why it takes time is because finding what A and B are, finding the scalar multiples of u and v that give me E1, and finding the scalar multiples of C and D of u and v that give me E2, that is a problem that's not straightforward. It's not like you can just shortcut your way through it. You can't. You have to do the actual due diligence of solving for A and B, C and D, so that you do find the scalar multiples of u and v, so that then it becomes straightforward. After that point, this is straightforward. It should be at least. Okay. Okay. Okay, great. So now we've talked about linear transformations, and we're going to continue talking about linear transformations, but now I'm going to talk about particular examples of linear operators. So I mentioned this to another student before. And I mentioned this to you guys earlier about linear algebra being very theoretical and applied at the same time. As you can see, there's a lot of application to it, and then all of a sudden there's also a lot of theory. Like the theory just pops up like crazy, and then so does the application. So sometimes it's hard to keep track the pure part of it, the theoretical part, with the applied portion. A lot of this is very theoretical because you're kind of like maybe not too clear, right? What do you mean by n-dimensional space? The notation here also might be a little weird because now you're plugging in vectors as an input, and you're getting another vector as an output, and the dimensions may be different. So you're like, wait, this is kind of strange now, right? Now you're dealing with something that you may probably never seen before. And so trying to look at things from a theoretical perspective as transformations are, right? From R2 to R3, from R4 to R5, like what does that really mean? Like what are we doing? So this could be like a whole bunch of gibberish to some of you. Like, I don't know, this is just like A, B's, and C's. I see a whole bunch of letters. You're like, wait, what's going on, right? So sometimes it's good to see these transformations as concrete examples. And then hopefully you start to see, oh, this is why linear algebra is so applicable, so useful, because for example, it can be used in a variety of applications, and we can get into that another day. But for now, let's look at the very basic, simple examples of how these matrices, which are associated with operators, how they really matter geometrically speaking, which is the first way of saying things apply, right? So we can see these things apply. So what's one of them? What's one type of linear operator? They're called reflection operators. Reflection. Reflection operators. So you guys have done this in geometry classes, for example. You've done a reflection, right? You've done reflections about, for example, the x-axis. Now, can somebody tell me what that looks like if I'm given a vector x, y, right? So, or in other words, x comma y. So see that this is where things get a little bit theoretical, right? The theory is that if you have a coordinate x comma y, and I reflect that coordinate x comma y across the x-axis, what's the new coordinate?
It would be negative xy.
About the x-axis.
Oh, so opposite. X negative y.
Right. Correct? That would be it, right? And so geometrically speaking, right? Geometrically, what does that look like? Well, this is y, this is x, right? So if I have a vector somewhere, x comma y, and I reflect it across the y-axis, I get this, right? This is x, this is y, this is negative y. So this would be x comma negative y, right? So that would be the reflection. So we understand what the reflection would be. Now, what does that look like as a matrix though? So how would you find the standard matrix? Remember, this is an operator. This is a linear transformation. What's the standard? But no one tells you that. No one says, hey, this is a linear transformation. No one's going to talk about that because of the theory that you need to get to, right? So what's the standard matrix? A of T. So remember, how would you? No, actually, Tassif, don't worry. It won't be messy. it will be actually simple. And hopefully you start to see, oh, really? Hopefully. So how do you find the standard matrix again of any operator, of any transformation? You need to apply what to that transformation? We talked about it in like the first few examples.
The E.
The standard basis, right? So what happens to E1? And it shouldn't be hard. What happens to E1 when you reflect it across the x-axis?
Nothing.
Nothing. It's the same, isn't it? So isn't this 1, 0? And then what happens when you reflect E2?
You just switch the sign for the one.
what? For what?
So it's 0, -1.
Correct. 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 So then what would be the matrix associated with the operator of reflecting across the x-axis? A would be what? It would be 1, 0, which is T of E1, and 0, -1, T of E2. Doesn't this make sense? It should, because if you take any vector, take V, right? And apply 1, 0, 0, -1 to this vector V, I'm gonna call this vector V XY. What do I get as a result? Don't I get what I'm supposed to get? I'm supposed to get X -Y. So the new thing behind all of this, which you already know or should know because you took geometry, is that when you reflect X, Y across the x-axis, you get X -Y, right? Which means this geometric illustration, which makes sense, right? And what the real new thing that you haven't seen yet is that whole process is really a multiplication of the matrix 1, 0, 0, -1 to any vector X, Y. That is the new thing. That is it seems suspiciously simple. Yes, that is the new thing. It's supposed to be simple because this is a simple operator. This is a simple transformation. You're taking X, Y, and you're transforming it to a new vector X -Y. But what does that mean from a matrix perspective? It means that you're multiplying the vector X, Y with the matrix 1, 0, 0, -1. Any vector you give me, I don't care what it is. When I apply it to A, I get the correct vector which represents the reflection of that vector across the x-axis. Does everybody follow that? So this is where matrices, linear algebra comes alive. Okay, so then of course, we don't stop there, right? We're not going to stop at reflections across the x-axis. We're going to go to the next one, reflections across the y-axis. So what happens with the y-axis? If I take a vector x, y, or xy, right, x, y, x, y, when I reflect that vector across the y-axis, what am I going to get?
-XY.
That's right. So what that looks like, I got the y-axis, I got the x-axis. I have a vector somewhere in space, xy. This is x, right? This is y. If I reflect it across the y-axis, I get another vector here. Mirror image, right, of the vector that I originally have. But now that the x coordinate is on the second quadrant, this has to be -x. So this coordinate is -xy. So we understand that, right? That's the geometric understanding of reflecting across the y-axis. Now, how do I figure out the associated matrix of this operator, linear transformation? I need to figure out what happens to the standard basis vectors when I apply this operation on it. And what happens when I plug in E2? So E1 is 1 comma 0. What happens when I reflect 1 comma 0 across the y-axis? Yes, Baldwin?
I just have a question to see if I'm understanding. So in this particular reflection, the basics vector number 1 is the one that's gonna get negated, right?
Yeah, in this case, the -1, right? It's going to be 1 comma 0. So it's like taking this vector. I'm doing this. I'm taking this vector and I'm reflecting it across the y-axis. I get this, right? So 1 comma 0 becomes -1 comma 0. And what happens when I take E2? E2 is up here, 0 comma 1. What happens when I reflect this across the y-axis?
It's the same, so 0,
It's the
1,
same in this case, right? So this becomes
0, 1.
0, 1. And so what's the matrix? -1, 0, 0, 1. Apply this matrix to any vector in R2, you get the indicated vector that's reflected across the y-axis. That's the idea. So if I take A and I take V, some vector, so -1, 0, 0, 1, and this vector x, V, I call it x comma y, right? This gives me -xy. That's the idea. So any vector that I apply this matrix on the left side, when I multiply by that matrix, I get the indicated vector that's the result of reflecting it across the y-axis.
So
So now, in addition to what you understand geometrically of reflections, now you understand that matrices represent that same transformation now. Yes, Baldwin.
I just have a quick question. So that matrix A, that's essentially the formula for a reflection across the y-axis.
Yes, yes, yes. But now you have a different way of visualizing it, understanding it. You're
Yeah,
dealing
like
as a vector. You're dealing with vectors, applying it to matrices, left multiplying it to those vectors, and then you get a new vector. Before linear algebra, you just saw, oh, reflect, take this one thing, and then put it on the other side, and that's it. Switch
like
the x and y's, or negate the x or negate the y, right? That's all you thought about.
Mhm.
But now you have an additional way of thinking about this, which is matrices. And once you have this kind of understanding, it becomes very powerful, because you can program this stuff. And that's another whole conversation in itself for those computer science people out there, because there's a lot of matrices involved, and you can a lot of programs, you can exploit the structure of matrices, right, to your liking. And then if you really want to get in depth with this, you can talk about computer graphics, you can talk about video gaming, you can talk about image processing. Sadly, we won't be able to do that here. We're just going to understand like the very, basic ways that you can build upon so you can get to that level where you can do those things. But anyways, for now, we're just dealing with reflections of a vector across axes. So we got the x-axis, we got the y-axis, and there's one more, right, that we talk about in geometry: reflection across the line y = x, right? So it's this line here. So when you have a xy plane, you have this line that goes down the middle diagonally. Sorry, this is y = x. So what happens when I have a vector x comma y? What happens when I reflect this across the line y = x? Does anybody remember what happens when I take x comma y and I reflect that vector or that point across the line y = x? Yeah, that's right, Sam. You switch, right? You switch. You swap the x's and the y's. So you'd have something up here. So this is my y, that was 1 to y, now is my x, and then my x, that was 1 and x value is now my y value. Now, what does that look like as a matrix? That's what we care about. So T of E1, 1, 0 becomes 0, 1. It becomes E2. And what happens when you plug in E2? It becomes, well, 0, 1 becomes now when you swap it, 1, 0, which is E1. Huh, so then what's going to be the matrix? 0, 1, 1, 0. Looks like the identity, doesn't it? It's just that the identity matrix, you just switch the rows, row 1 and row 2. So see, so if I would have just showed you this matrix 0, 1, 1, 0, you would be able to multiply it and be, oh, yeah, that's what I get. But now you have a visualization geometrically of what that is when you multiply by x, y. Like when you multiply this by a vector, what do you get? You get what would happen if you take that vector and you reflect it across the line y equals x. So now this matrix means more than just zeros and ones. Now it has a geometric meaning to it. And in a sense, it becomes much more valuable now. Hopefully you start to see that. Does that make sense? Any questions about reflection operators in R2 space? No? Clear? Is this clear now? We're starting to see now the connection between matrices and geometry and transformations, how they're all connected. Okay, so that's reflection, right? But then what else do we have?
Dilations.
Dilations. Yes, we do have dilations, but we're not going to discuss dilations per se. We're going to discuss projections. So number 2, projections. So a projection, right? Sorry, so this is operator. It's another table. We're gonna have the illustration, and then we're gonna have the geometric understanding of it. And then we're gonna have the associated matrix. This is A, this is T, right? So there's something called the orthogonal projection. Not sure if you guys have all heard of this. The orthogonal projection onto the x-axis. So that takes the vector xy. Does anybody know what it does to it? What does orthogonal projection mean? In R2. So if I have a vector somewhere in space, x comma y, and I want to project it, quote unquote, project it onto the x-axis. Does anybody know what that means? Orthogonally project. Does it mean to move it to the right? No, actually. So this is sometimes talked about, most of the time talked about in multivariable calculus when you have to project vectors. Find the orthogonal projection of a vector. So think about having an object that just like sticks out in this diagonal, right? And you're projecting light. Like there's a light source right above this, and it just beams down directly above it. And make believe this is like a table or the ground or something, right? So when you have a light source here and you project it and you beam it down, right? Wouldn't it cast a shadow? And basically that shadow that's projected onto this ground screen or whatever, right? This here is your projection. So then if this is x comma y, right? I'm projecting it onto the x-axis. So my y value is no longer y, it's 0. And the x coordinate is exactly the same x coordinate as my original vector. So this will have the coordinate x comma 0. And this would be the orthogonal projection. So if I call this v, right? Then this would be the orthogonal projection. Orthogonal projection of v. Does everybody see that? And the orthogonality, what does orthogonal mean? It means perpendicular. So these two vectors, if you see this, like the components that they call them, these components of this vector, the horizontal component and the vertical component, they have to be orthogonal, or in other words, perpendicular. So x comma y becomes x comma 0. And so then t of E1, what's t of E1? We'll take E1, this vector here, and project it onto the x-axis. It just becomes what? 1, 0. It's just itself. E1, when you apply this operation to it, gives me E1 again. Now what happens when I do E2? What happens when I do E2? And I project this vector onto the x-axis, right? It becomes nothing. It like shrinks into a little point because there is no horizontal component to it. So this becomes 0, 0. So then what is the associated matrix of this operator? It is 1, 0, 0, 0. And this is my associated matrix. So when I see the matrix 1, 0, 0, 0, it's not just any matrix. This matrix, when you left multiply it to any vector, does what to it? It produces the orthogonal projection of that vector onto the x-axis. Make sense? So then, of course, we're going to talk about not just the orthogonal projection onto the x-axis, we're going to talk about the orthogonal projection onto the y-axis.
Wait, Professor, just to kind of get this from my head, the orthogonal projection to the x-axis basically shrinks the y-axis, and then I'm guessing
Basically eliminates the y-axis, yes.
and then the opposite for this one that we're about to do.
Right.
Okay.
Right. Right. So then now in this case, we have t of x, y, right? But by the symmetric argument, the result will be what? 0 comma y. Because I'm going to have the same illustration. Got the x and the y axis. I have some random vector, right? V, call it xy. But now my light source is no longer directly above and projecting it straight down. Now it's like on the side and I'm projecting it straight to the left. And when I'm doing so, the shadow that's cast onto the y-axis is just a vertical component of that vector. And this vector is going to be what? 0 comma y. So this is the orthogonal projection of V onto y-axis. This is onto the x-axis. So what happens to E1 under this operation? It becomes what? 0, 0. What happens to E2? Well, you project 0, 0, 1 onto the y-axis, you get 0, 1 again. And so then what's the associated vector to that? 0, 0, 0, 1. And sometimes people just call these projector matrices. So you can put them as a P instead. These are examples of what are called projector matrices. Any questions about these operators, the geometric understanding of those operators and their associated matrices? Is this starting to make more sense now? Why we do E1, E2? Because once we know what E1 and E2, what happens to those two vectors, we know what happens to every other vector, because it happens to those two first. And I can express every other vector as a linear combination of those two standard basis vectors. Does that make sense?
Yes.
Any questions?
I have a question. I
Yes.
was looking through the book and they talked about orthogonal matrices. So P would be an example.
Oh. No.
Oh.
Yeah, so be careful. So that's the thing. Okay, so sometimes there's confusion between the same words that were used. Like, what's that called in computer science? When you have a word that, I forgot, there's a word that like there's some words that have a specific meaning, right? And you can't use that same keyword for something else.
Oh, yeah, I know what you're saying.
Like ambiguity. I don't know if there's another term for that. You guys may know that. But like orthogonal projection is not the same as orthogonal matrices.
Okay, so they're different.
Yeah. So these are projection matrices. They are not orthogonal matrices. Orthogonal matrices has a different, distinct definition. We haven't spoken about that yet. Orthogonal matrices are matrices whose transpose are inverses. So if I have a matrix and I find its inverse and I apply it, no, if I have a matrix and I find its transpose and I multiply the transpose of the matrix to that matrix itself, I get the identity, which means that the transpose of this matrix is the inverse of that matrix. If that's so, that matrix is called an orthogonal matrix.
Okay.
These are matrices that produce the orthogonal projection of a vector, which is not the same thing. It's like two different. The word orthogonal is used in both. The P is there too as well, but it's not the same thing. So don't worry about orthogonal matrices. Worry about projection matrices, which represent the orthogonal projection of vectors onto different axes. So I know it's hard to like see the difference because of the wording. The wording is very similar, but they're not the same. Very good. Yeah, orthogonal matrices are very important too, but these are projection matrices, which represent orthogonal projections of vectors. So I just want to make that clear as day. Okay. So we have projection operators. We got reflection operators. And there's one more, which I think is more fun than the previous two. So we're not going to talk about dilations because I don't think there's much to that. I think dilations are just the identity matrix being multiplied by a scalar. But the next, so there's reflections, there's projections, and there's one more. If you do guys remember, it starts with an R as well. One kind of transformation that appears a lot in geometry. Alexa, that's right. Rotation. Rotation operators. And of course, these operators are in R2. We're doing R2. So, I want to rotate. So what's the operator, right? What's the geometric illustration? And for this problem, for this example, actually the geometric illustration helps a lot. And the other two, it's kind of like you don't really need it. You can visualize it yourself. But for this one, the geometric understanding actually helps a lot. And piecing together what the associated matrix would be and how that's connected to the operator. So I want to rotate. What do I want to rotate? I want to rotate. What is it? Rotate XY counterclockwise. We love going counterclockwise. Counterclockwise about the origin. By what? Or through an angle. Through an angle. Theta. Right? Normally we say, oh, I want to rotate this coordinate 30 degrees about the origin. That's normally what we would say, right? Now, how do we interpret that? How would we interpret that? And this is when circles really become important. So here we have a circle. We got y-axis, we got the x-axis, and then we have a point on the circle. And we have theta. Well, actually, yes, we have theta. We have theta. So we have the coordinate here. We have a coordinate x comma y, right? And we want to rotate this vector or this point. I want to move it theta degrees about the origin. All right, so I want to rotate this somewhere differently. Now, so you see how I haven't defined this yet. I haven't defined it yet. I haven't defined this yet. But I know that this will be x comma y, right? This will give me something. And what is that something? Well, let's think about this using E1. Because that should be simple, right? And E2. If I know this, I know everything. If I don't know this, I don't know anything. So let's draw this again. Let's draw this again. This XY plane again. I'm gonna draw a circle again as well. But now I'll be very specific. I'm only going to be looking at E1. So look at E1. 1 comma 0, right? I want to rotate this by theta. And hopefully something starts to spark in your head. If I rotate this by theta, do you guys know the new coordinates?
Would it be cosine? Something cosine.
Yeah. Remember you guys talked about this back in the trigonometry period of your time of your life? So Mahmoud says x equals sine theta. The dark age. Y equals cosine theta. Are you sure about the x-axis being in sine theta? So if you don't remember, it's okay. Think you can reason this out every time. Just extend this, right? Extend this down downward, like a projection. And then what do you have? You have a right triangle. So to understand circles, you need to know triangles. To understand triangles, you need to know circles. They come hand in hand. So when we want to learn about circles, actually understanding triangles helps a lot. Because if this is a unit circle, which it is, because this vector here is 1, 0, so the radius is 1. So all the way around this, it's 1, right? So this has to be 1. The radius of this hypotenuse of this triangle is also 1. And if this has the coordinates that I don't know, call it x, y, right? Then when I project it across the x-axis, this is x. And when I project this across the y-axis, this is y, right? So then what do I have here? I have a right triangle whose dimensions are 1, x, and y. So what is x going to be? Well, if you use trigonometry, sine, cosine, theta, right? SOHCAHTOA. So this is the adjacent side. X is the adjacent side to theta. And 1 is the hypotenuse. So then this x here really is what? This x comma y really is what? Cosine of theta. And then the y coordinate, well, that's the opposite of theta. So opposite theta, and you know the hypotenuse is 1, it would be sine. Sine of theta is y over 1, which means that y is sine theta. So guess what? When I transform, or when I apply the rotation operation to E1, I get what? Cosine theta, sine theta. Do you guys see that?
Yeah.
So this is E1 again, right? This is E1. Now what happens to E2? Call this E2. This is what? A 1, right? 1. This is E2. I want to rotate this what? The same thing. Theta units this way. Now this is a little bit different now, right? Now I'm applying it this way. I'm applying it from here and I'm going in this direction. But in reality, this triangle here and this triangle here should be the same exact thing because I'm taking the same vector. I'm just placing it in a different position and I'm applying the same movement. Of course, not drawn to scale, of course, right? I'm not the greatest artist here. Let me try this again though. So if I do this, whoops. Do you guys see that this is the same exact triangle? It's just that now it's in the second quadrant. And then what did I say that this equal? What does y equal here? Y equals sine theta, doesn't it? And what does x equal here? Cosine theta, doesn't it? Right? So then wouldn't this also be sine theta? And then wouldn't this portion here also be cosine theta? Because it's the same triangle. Does everybody agree with me? Isn't it the same triangle?
Yeah.
But what are the coordinates of this new of E2 after I've applied it? What's this new coordinate here?
Would it be sine, cosine?
Not sine. I'm in the second quadrant. So the x coordinate has to be negative.
Oh, so negative cosine, sine.
Not negative cosine. It's negative sine. Why is that? This here represents the x-axis. You see how the length of this triangle is the same here, right? Sine theta. But now I'm in the second quadrant. So this distance here, whatever this is, I just put a negative to it. And then the y-axis is this part of the triangle, which is this part of this triangle here. The y-axis on the y coordinate is the same thing as the x coordinate of my new rotation of E1. So when E1 is rotated, my x coordinate is cosine theta, right? Because this is my x coordinate here, and this becomes now my y coordinate, cosine theta. Do you guys see that? And so now this becomes negative sine theta, cosine theta. Yep, trig. Hey, people don't like trig, but with trig, without trig, you can't do all this cool stuff, man. You can't. You need trig. Very useful trig. Trig is super useful. Now look at this. So then what is the the associated matrix A with rotation about the origin through an angle of theta degrees? Now it's very simple, isn't it? Yes, Baldwin.
I was gonna answer to see if I understand it.
Please do.
Would it be cosine, negative sine, sine, cos?
So you did this cosine, negative sine,
Yes. And then sine,
sine,
and then
cos.
cos.
Correct. Because this is the first column, second column. It works out. So then every single time now, this is my rotation. This is a rotation matrix. So now you start to see, oh, there's different kinds of matrices. You talk about non-singular, singular, invertible, non-invertible. And then you start talking about diagonal matrices. Then you talk about lower triangular, upper triangular. Then you start talking about projection matrices. Then you start talking about reflection matrices. And now you're talking about rotation matrices. There's so many different kinds of matrices. So whenever you apply a vector to this matrix A, what would you get? You get cosine theta, negative sine theta, cosine theta, and I'm multiplying this by xy for a given vector. So the result would be what? X cosine theta minus sine theta y is equal to x sine theta minus y cosine theta. Let me write this y in front. So you see how it wasn't that simple to write the operator first? Because what does it mean to rotate a point about an angle theta if I'm just given x and y? They never taught you this. They never taught you how to do that, right? I think they only taught you how to do, if they teach it, they only teach 90 degrees, like how to rotate around 90 degrees. They don't do 30 degrees. They don't do 45 degrees, 60 degrees, any other of those degrees. It's only 90 degrees, 180 degrees, 270 degrees, and 360 degrees. That's what they teach usually in geometry. So then what would be the operator for this? It looks like a complicated, it looks like a complicated expression, but I hope now you see why this would be the formula, because of this idea of matrices, transformations. So when I get xy and I want to rotate this point xy, this vector xy, about counterclockwise about the origin through an angle of theta, what do I get? I get x cosine theta minus y sine theta. That's gonna be my I'm gonna write it this way, guys, because there's not enough space. I'm gonna write it in landscape form. So if I've applied txy, I guess for now I'll just rotate this as well. So there's a whole bunch of rotation going on. See that? I can do that. So then t of xy is x, what is it? X cosine theta minus y sine theta, comma, x sine theta minus y cosine theta. And this would be the formula. Let me rotate this back. Does everybody understand what's going on with this? Craziness, right? It looks crazy, but isn't it cool now? Like now this whole idea of matrices seems to be a bit more useful. Like now it's not just merely solving system of equations. It's not just merely, oh, we have columns and rows of numbers. And it's not just merely, oh, I'm going to find the inverse of a matrix. Yay, whoop-de-doo. Like it's not merely that anymore. It's, oh, this matrix, you can have theta in it. You can have trig with it, but then like, how does trig relate? How does that even work? Like, how does that connect with geometry and then geometry? Like, so now you have more understanding of why these matrices matter, why we study it. And there's a slew of other applications, but this is just like one, just one little thing. Okay. Okay. So let's use this as an example. Find the image of the vector 2, 3 under a rotation of pi/6 radians about the origin. So what would be how would I approach this? I have a vector 2, 3. I want to know what it looks like. What would be the vector if I were to rotate that vector 2, 3, pi/3 radians about the origin of course, in a counterclockwise direction. So what do? We should first find the rotation matrix that rotates, right? pi/6 radians about the origin. So what would be that rotation matrix? We can call it R for rotation. Well, we just talked about rotation matrices, right? I think let me reshare my screen. Something's up. Okay. So what would be my rotation matrix? Well, I have the rotation matrix in general for sine, right? It's cosine of the angle, negative sine of the angle, sine of the angle, cosine of the angle. But my angle is pi/6. So you guys have to remember, what's cosine of pi/6? What's sine of pi/6? What's negative sine of pi/6? What's cosine of pi/6? Does anybody remember?
So pi/6 is 30 degrees, right? If you
Correct. So this is 30 degrees. Yes. So then cosine of 30 degrees would be what? Does anybody remember? You guys should know this. It's trig at its finest. No? Cosine of pi/6?
Off the memories of trig years ago.
Oh, okay. It's rad 3/2. Sine of pi/6 is 1/2. So then you know everything else. So this matrix is not just a random matrix. It's not just random anymore. Now this, when I apply a vector, RV in this case, when I apply rad 3/2, negative rad 3/2, 1/2 rad 3/2, it's not going to be a pretty number. It's not. But whatever it is, right, this becomes 2 times rad 3/2 minus 3 rad 3/2. This becomes 2 times 1/2 plus 3 rad 3/2. If you cancel out, you get rad 3 minus 3 rad 3/2. You get 1 plus 3 rad 3/2. That's my new vector. And just to like approximate it, just to see what the actual
Professor,
yes.
Sine 30 degrees should be 1/2, I think.
Oh, that's right. That's right. I just rewrote that wrong. Sorry, pardon me for that. You're right. It is 1/2. So that changes stuff here a little bit. So this should be -1, right? So this is rad. No, this is 1/2 times 3. So this is 3/2. And then that's all it changes, right? Yeah. So yeah, thank you. I don't know why I wrote rad 3. Over 2, it is 1/2. Sine of 30 degrees, sorry, sine of pi over 6 is 1/2. And cosine of pi over 6, which is cosine of 30 degrees, is rad 3 over 2. So then when you find just the just the approximation of it, this would be 0.232. And then this would be, the y coordinate would be 1 plus 3 rad 3 divided by 2. I would get like 3.598. So if I were to plot this vector, it would be a rotation of 30 degrees about the origin for 2, 3, whatever 2, 3 is. So let me just try to see what that would look like. Try my best, of course. Let me see if I can dotted paper. All right. So 2, 3, I'm gonna write this like this: 2, 3. Oops. Okay. So this would be 1, 2, 3. This is 1, 2, 3, 4, right? This is the y, this is x. So then I have the original vector is 2, 3. So I have something like this. And then my new vector, this is v. V is 2, 3. And then my other vector would be 3.56. So somewhere like 3.6 around, somewhere like right here, and 0.2, like somewhere like right here, probably 0.5. 0.2 will be somewhere here. So my new vector will look something like this. Let's see. Oh no. It's not gonna be the straightest line in the world, as you can tell. So this is when hold on. Okay, it's not gonna. Right, something like this, right? This would be the rotation of V, which would be around 0.2, what is it? 0.232 and 3.598. So this apparently, this rotation here was 30 degrees or pi over 6 rad. Okay, I try to do that. I try to do it best of my ability. A -1/2. Yes, that's right. That's right. -1/2. Did I write that? Yes, I did. Okay. Good. Good. Does anybody see that? The utility of let me stop here. The utility